All right, thanks, Ben. Yeah, I'm here to talk about gwpy, which is, you might have seen flashed up on the screen before. It's a Python package that I've developed along with a lot of other people to do, kind of simplify a lot of the boring / annoying bits of reading, writing, processing data in LIGO. The talk carries only my name, but it is really a accumulation of work by a fair number of people, whether they wrote code or whether they debugged code or whether they gave up ideas. So don't take it as this is my work alone. As Ben said, I'm coming out of Cardiff University, where I'm a research fellow, where basically I get paid full-time to do this kind of software development, which is very exciting for me. So I need to thank the Welsh Government, etc., for paying for the funding. Right. The first question that we haven't really asked ourselves, which is important to ask, is why Python as a programming language? We could do this in a large number of other ways. Historically, in astronomy and astrophysics, a lot of people have used MATLAB and IDL and similar tools. The most important thing is that Python is free. It also comes available on most of your Unix machines, so it's free and you don't really have to think to get it. The other important thing is that it looks like pseudocode most of the time. So you can kind of write plain English and it will probably do what you want. As I say, it's already widely used in astronomy and astrophysics already, which means that a lot of the work is already done for us. We don't need to start from scratch a lot of the time. And again, the most important thing is it's free. And it kind of sounds silly because a lot of us are coming out of universities where they're paying for MATLAB and other tools already. But this is really the key to getting much wider adoption of these tools outside of academia and down to the more kind of entry-level sort of high school students and stuff who just don't have the money to pay for these resources. So this is really, really important. All right, let's talk about gwpy itself. It comes with a kind of a silly tagline, which is a Python package for gravitational wave astrophysics. It doesn't do actually an awful lot of astrophysics, but it does simplify a lot of the annoying things that you might need to do. This is the website, gwpy.github.io. From there you can find links to the documentation and links to the GitHub repository and that kind of thing. It's heavily dependent on packages called NumPy, SciPy, AstroPy, and Matplotlib. If you've used Python before, you're probably familiar with some or all of these. If you're not familiar with Python at all, this is array algebra, this is signal processing, this is some astronomy tools, and this is plotting, and that's it. The way that it's structured is that it provides intuitive, object-oriented methods to access the data, both public data, as we'll talk about today, and restricted data for members of the collaboration, also to do some processing and to do some visualization. The fact that it's object-oriented is just, it's important to realize that's the way the code is structured, so that's kind of the way you interact with it. But it's not too important, but hopefully we'll get into a little bit more of that this afternoon when a lot of the tutorials are gwpy based. Another important thing is that nothing in the code is really specific to gravitational wave data other than the data access routines. But as soon as you have data in there, it's just signal processing of a time series or a frequency series. So a lot of the tools are generic, which means that they're not novel ideas, they're just kind of simplified in this code base. Spend a little minute talking about the way it's used in the LSE and Virgo at the moment. It's available to all of the users on what are called here the LIGO data grid machines. These are just the shared computing clusters that all of the LIGO Virgo collaboration members have access to, which means that people don't have to know how to install the software and all of its dependencies. It's just already available for them to use. Historically, it's been widely used in detector characterization, first and foremost, because that's kind of my research background. We use it to do daily data summaries, which Jess mentioned already. Detector and environment noise analysis, as Jess mentioned already, and to do data quality veto generation and testing. And this is to identify noise that the analyses can then excise before they do their processing. The I/O and the visualization parts are used in a few data analysis pipelines already, but as I say, this does the generic things well, but if you want to do matched filtering stuff, you'll hear more about that in other Python packages later in the week. A quick kind of side note on the summary pages. This is kind of where a lot of the functionality was born out, where we have these daily summary pages which are for internal use, where it's kind of a one-stop shop of information on detector status. There's nearly 1,000 figures of merit produced every day for each of the LIGO interferometers, talking about detector sensitivity, operating time, the quality of the calibration, also environmental sensors and some transient noise analysis stuff. So this is what's kind of driven the development, but it's nice to advertise, Jess mentioned it very briefly, the public-facing summary pages. So these are the URLs down here at the bottom. These are pages you can go to now and see the data from today, if there were any data. And included in there are power and amplitude spectral densities for LIGO and for Virgo, statements on the sensitive range to a binary neutron star and spiral. That's kind of our canonical source by which we measure sensitivity. Details of the operating segments, and then trends of some environmental sensors, including ground motion and the temperature and that kind of stuff. Again, there's the URL. The latency is maybe 2 or 3 hours, which means that if you go now, you can see the data from 2 or 3 hours ago. Unfortunately, at the moment, we're in an engineering period, so there's no kind of new observation mode data. But once we get back into 03, which will be at the end of the year, this is a really nice place to get kind of essentially up-to-date live information on what LIGO and Virgo are doing. All right, let's go through a very quick introduction to gwpy and kind of how you would use it. So let's have a quick show of hands. Has anyone never used Python before in their life? I see no hands. That's very good. So then most of you will probably know what this means. I'm not sure how visible that is. So to install this, pip is the standard tool that you use to install Python packages, at least on Unix machines. You can just do pip install gwpy and everything will come down and it will install itself. And that should pull in all of the dependencies and everything. So it's nice, very simple. The next thing you do is you import the class that represents the data that you want to study. And this is where kind of object-oriented terminology comes in. So most of the time we're studying time series data. So there's a time series object that you import from the time series module. So you end up with this time series object, which you can then use to request and interact with the data that you have. So let's fetch some open data publicly available from the Open Science Center. So the time series object comes with a method called fetch open data. So what you give it is your detector prefix. For historical reasons, we use the kind of first letter of the observatory's location, so H for Hanford and L for Livingston, and then a 1 or a 2, depending on which interferometer it is, because LIGO Hanford used to host 2 interferometers at the same facility. So we would have H1 and H2 and L1. So that kind of convention is still kept around. So for LIGO Livingston, you say, I want L1, and then you give the start time of your request and the end time of your request. This, you can see, ends up being 32 seconds of data. And if you remember your astronomy history, this is around the first detection of gravitational waves. These can also be given in GPS times, if you're very familiar with 10-digit numbers. But it's nice that you can give these as kind of human-readable times if you want. So what this will get you is, this will go away, it will use an API, which basically just means it will communicate directly with the LOSC server rather than you clicking through web pages. It will find the files that you want, it will download them, read the data, and then clean up after itself. And you'll end up with a time series object that you can then do many things you want with. The easiest thing is to make a plot. So it comes with a method called .plot, which returns a plot object. And then you can say plot.show to show you the plot. Hopefully all of this makes sense, and it's kind of pedantically put together in using objects rather than just function calls, but I think it makes it very clear what you're doing. So you load your object, you download some data, you create a plot, and then you show it, and this is what you end up with. So with, what was that, 4 lines of code, you've end up with a relatively nice looking plot. You have a nice time axis. This is kind of strain amplitude on the y-axis. You see we're looking at scales of 10 to the minus 18 here. We'll come to that in a second. And you see lots and lots and lots and lots of noise. 4 lines of code, you've got a plot that looks pretty good, but it's not so useful in terms of scientific analysis, but it's a very good start. And that's the main thing I try and push on with this code, is that it just simplifies all of the things of data access and some visualization so you can get to some science a little bit faster. All right, a little aside on data access. So we've seen that we can fetch open data from the Open Science Center. You can also just read data directly. If you happen to have a file on your file system that does stuff, you can use GWF, or you can transparently use text files or HDF5 files. It kind of doesn't really matter. It will work out what you're trying to do and try and do it automatically. As we saw that you can query open data, this is an example using the Hanford prefix H1 and then some GPS times, so it's basically the same call as we had before. And then LIGO Virgo members can do something a little bit more involved, where they can use this internal query, which requires you being an authenticated member of the collaboration. You do the same kind of thing, where this time you use our data channel names, which are a little bit more specific, but it gives you access to the full suite of HFT and all of our auxiliary instrumental environmental sensors. As it's been mentioned a few times before, these are not publicly released, at least not yet. There's discussions on kind of how to do this. The main problem is, how do we store this much data? Dave mentioned that we have over 50 megabytes per second, so just releasing that into the wild is quite a kind of technical challenge. And also documenting what all these things mean is a problem. So hopefully we'll get there, but it's a lot of work to do this. So these are some pointers on data access. Hopefully it's all fairly intuitive. We're going to talk a little bit about signal processing. I'm not going to go into much detail. I'm intimately aware that we're closing in on lunch, so people will start getting a bit growly. So I'll go through some very quick examples of how to do these things. The kind of raw gravitational wave strain, as we've seen, isn't very useful for making pretty plots. So if you want to do this kind of time domain analysis, you want to do some simple signal processing, including maybe band passing, where you knock out some low frequency and some high frequency noise, or just low passing and high passing. We're going to talk a little bit about notching, which is where you excise specific frequencies. There's also the ability to do arbitrary filter definitions using the zero-pole gain format. If you know what that is, that's good. If you don't know what it is, it's not really important for now. Just to say that there is functionality available for you to be as specific as you want. So let's talk about the signal processing. So you do this fetch open data call. Here you see there's 32 seconds of data, but what I've plotted here is just 0.6 seconds. So it's just a zoom in of the same data, kind of unfiltered. But then if you apply a band pass from 50 hertz to 250 hertz, there's just a dot band pass function, you get, this is the same time, just with some filtering applied. The scales have gone all the way down to 10 to the minus 21, which is much closer to our kind of strain amplitude. And you get something that, there's still a lot of noise in here, but oh, maybe over here there's something significant. So we think, right, I remember from Dave's talk and from Jess's talk that one of the big features in our power spectrum, in our frequency domain, is that we have lots of kind of noise corruption from the 60 hertz power mains from the US power supply. So let's notch that out and see what we get. So you apply a notch filter at 60 hertz to say remove the noise at 60 hertz. And this is on top of the band pass you've already applied. And this is what you get in that 0.6 second span. And it's what, to people like me, looks like a really clean noise time series where there's very low noise. It's kind of random statistical noise. And then there's something very significant that looks a lot like a gravitational wave signal. And this is the gravitational wave signal from GW 150914, the very first detection that we made. So with just a very small amount of code, you can get down to this kind of level. Obviously, there's a lot happening in the background, but some kind of sensible default choices for how you do your filtering have been made so that you can kind of get this far without knowing like digital signal processing inside and out. If you go a little bit further, you can add in data from the other detector, and you can kind of shift things around to make a very nice plot showing information from two detectors. It's all lined up, and there's clearly something statistically significant in here. If you go to this URL, this is get.io/gwpy-gw150914-simple. That's a link to the code that was used to make the plot. It's 30 lines of Python. It is indeed 24 lines of Python. So yeah, so there's 3 lines of input-output, just 1 line to import your object, download data from Hanford, download data from Livingston, 9 lines of signal processing, and then 12 lines of plotting. So most of the work required is to make the plot look good, which I think is quite nice. Talk a little bit about signal processing in the frequency domain. A lot of people have mentioned the idea of Fourier transforms, and especially the fast Fourier transform, which is just a kind of digital implementation of the Fourier transform algorithm. gwpy will allow you to do that. There's just a .fft method of your time series. This is what you get if you run .fft on the time series we downloaded before, and it looks terrible. This is because this is kind of not what we do in LIGO analysis. If you do an FFT, you'll end up with all sorts of effects because you've got boundaries at each end of your time series, and it just doesn't look very good. So what we do in LIGO analysis to produce nice, smooth amplitude spectral density or power spectral density estimates is we do windowing and overlapping. I'm not going to go into a lot of detail. This is a plot I stole from the internet, so don't. You can go here to find the actual source for the figure, the credit. But this is the idea that you use a window function to kind of smooth off the edges, and that removes some digital artifacts. And then you overlap your Fourier transforms so you can take into account all of the data. Obviously, if you do a windowing, you're basically zeroing out the data at the edges, so you overlap them so you don't lose the information in here because it's included in this next one. So you're doing lots of overlapping Fourier transforms, and then you average them all together, and it gives you a nice estimate of the frequency domain content of your signal, and this is what you get if you do that. This is called an amplitude spectral density. So there's a method here which just kind of does all of that for you. You say, I want to use an FFT length of 4 seconds, which will give me 1/4 Hertz resolution. It works out the best way to do the averaging and the windowing to give you something sensible. You can over-specify all of these things if you really want to, and this is what you get back. It looks a little bit more familiar in terms of what we've already seen this morning, but by default, it shows you the entire frequency range. Nobody really, up till now, has shown you below 10 Hertz because it looks terrible, but this is because our calibration isn't guaranteed below 10 Hertz. So we put a large high-pass filter in, which kind of cuts off the amplitude. This is not scienceable data, if I can invent a word. But down here, we see the same kind of structure that we've had before. It goes down. We've got some radiation pressure noise and some Brownian noise from our optical coatings, and then we have shot noise bringing it back up. And then this large feature here is the impact of downsampling your data from 16 kilohertz to 4 kilohertz for LOSC. The filter doesn't give you everything up to 2 kilohertz, which is what you get back, but it kind of rolls off at around 1600 hertz. So the impact of signal processing is very important to understand, and we'll get more into that in the afternoons. Did you have a question?
What does FFT length equals 4 mean?
The argument is this is how many seconds worth of data I want to use in a single Fourier transform. As I mentioned very briefly, if you know your kind of Fourier transform definitions, this defines the frequency domain resolution that you get back. So a Fourier FFT length of 4 seconds gives you 1/4 Hertz resolution, so there's a data point every 1/4 of a Hertz here. This is what you get if you add in some plot formatting options and you add in, again, data from the other interferometer, and it allows you kind of quite easily to make a nice plot. Again, strain noise versus frequency. This is much more familiar in terms of what Dave and others have already shown this morning. Again, there's a link to the code, git.io/gwpy-gw5914-ASD. The slides will be available later. But again, this is, I know, it's like 40 lines of code. All right. Quick digression into segments. Agatha already mentioned that LOSC hosts timeline segments. There is an interface to this. I'm kind of going to briefly skip over this. There's an object you import, you do a call, you do a plot, and you get this. All this shows you is that in this 24-hour period, this is the 16th of September 2010, you see that Hanford, this is H1 data, was operating for 1, 2, 3, 4, 5, 6 different operating segments in this day. This is important to note because in these red gaps, when Hanford was known to be not operating, the data are not available. That's the reason why we show this kind of stuff. Quick aside on data tables, there's kind of nothing in the tutorials we've got for this afternoon, but I thought I'd mention it in the slides so that it's there if people care. gwpy has some handles into data tables built on top of AstroPy, so thank them for the code. But you can imagine designing a little catalog of GW events. This is the content of our catalog.csv, meaning comma-separated values files. You have your event name, GPS time, mass 1, mass 2, and the distance. I pulled all of the numbers out of the publications that we've put out. So these are kind of public domain data, shown purely for kind of demonstration purposes. There are large uncertainties and small uncertainties on all of these numbers, so purely to show you what you can do with making a plot. But if you read through the code, I'm kind of going to skip over this a little bit, but you can import the table, you read the table, and then you can plot mass 1 versus mass 2. And there's some options for setting x-axis limits, y-axis limits, that kind of thing. And this is what you get. The idea that you've run 10 lines of code and you get a plot which shows you the distribution of component masses for our detections, and it's nice and simple. You might think that there's a linear trend up here, but if you plot everything with the full uncertainties, everything is actually consistent with M1 equals M2. So it's just an important note that uncertainties are important, and I haven't attempted to include them at all. Again, if you do something this is just an example of how you can create new columns. This is mass 1 plus mass 2 is a new thing that I've called MTuple. And then you can make a plot, and this is our distribution of total mass versus luminosity distance for the detections we made to date. All right, nearly done. All right, so that's kind of the end of my spiel. I've gone very quickly, so I apologize for that, but we have important lunch plans. This is a link to the documentation. There's a list of examples. There's something on the order of 20 worked examples with kind of explaining all of the lines of code and the results that you get. They go through two concepts that I haven't touched on, but Jess mentioned already this morning, spectrograms and Q-transforms. Here's an example of a spectrogram you can make. This is taken from the examples page. This is 10 minutes of data, I think, from the LIGO Hanford detector around GW 150914, and it just shows you the time variation of the frequency sensitivity of Hanford. You see that there are large peaks around 35 Hertz, and this is our calibration line, I think. This is the 60 Hertz power mains. It's pretty stable. There's some violin modes up here. There's some more violin modes up here, etc., etc. Down here, you can see that there's some big bump in the noise, some seismic event probably. But buried in here somewhere is an actual gravitational wave signal. Spectrograms are not the tool you would use to do that. Jess told you about our Q-transform, which does this kind of three-dimensional decomposition into time, frequency, and Q. And if you do that transformation on, I think, the same data, you get something that looks like this. This is a completely different time scale. This is milliseconds on the x-axis now. But you can do this decomposition. It's, 25 lines of code or something. And you get this beautiful track of a binary black hole in spiral. So this is just an example of, you can make these pretty plots very, very easily. I want to close on a note about contributing, and this is very important because a lot of people have this conception, a misconception perhaps, about code in these large collaborations like LIGO and Virgo, that the code is our code, and you can't possibly contribute to it because it's our product, and this is total nonsense. gwpy is an open source library hosted on GitHub, which means that any of you can see the code, any of you can copy the code and play around with it. It does have a license, which means that the kinds of things you can do are prescribed in the license. It basically says you can kind of do whatever you want as long as you make your code open source as well. Anyone can report problems, post questions, or suggest new features, and anyone can post bug fixes, improvements, or new additions. And this is really important. So any of you can take the code, you can kind of play around with it, mess around with it, and contribute back, and that will actually impact the science we do inside LIGO, because this code is used inside and outside. And just a note to say that there's no such thing as a silly question to post on here. It's kind of a cliche, but it is actually true. Chances are, if you have a question about the code, it's not your fault in terms of a misunderstanding. It's our fault because we haven't documented it very well. And there's also no such thing as trivial contribution. I take great pride in pushing back to other packages one character changes in their documentation because they misspelled a word by accident. That's just who I am. Last thing is a link to the code. This is the GitHub repository, github.com/gwpy/gwpy. I think that's all I have. Just a point to say that gwpy is a nice library. I've put a lot of effort into it, but it's kind of not what we use to do our real hardcore signal detection. And this is a plug for Alex's talk and other talks in the further days. gwpy is heavily used in detector characterization, but it doesn't do matched filtering and that sort of thing. So there's more to come on that tomorrow. Do I have more slides? I don't have more slides. All right. Thank you very much. If you have questions. Nailed it.